In our last video of this section, I'd just like to get a little bit more practice finding vertical and horizontal asymptotes because it is a skill that we're going to need to come back to later on in the course. So I really want to make sure that we have that down. So it doesn't matter which we start, if you want to start with vertical or horizontal. I'm going to start with vertical asymptotes here. Now, if we're looking for vertical asymptotes, the very first thing I'm going to do is try and factor my function if it's possible. It's not always going to be possible. But if I look at my numerator, x squared minus 9, that's a difference of 2 squares. So I can rewrite that as x plus 3 times x minus 3. My denominator then, let's see, I need two numbers that multiply to be negative 12, add to be negative 1. Those would be x minus 4 and x plus 3. So remember, if we have a common factor that cancels from your numerator and your denominator, in this case we have x plus 3 that we can cancel, that is not a vertical asymptote. That would tell us the location of a hole. So remember, that would tell us the location of a hole. So in this case, we don't need to do anything with that x plus 3 if all we're interested in is asymptotes. So after we do some simplifying, we're going to end up with x minus 3 over x minus 4. Any leftover factors in your denominator, which in this case is x minus 4, we'll take that and set it equal to 0. So x minus 4 equals 0, and we'll solve for x. In this case, we end up with x equals 4. So this is my vertical asymptote. I have one vertical asymptote at x equals 4. It is possible, remember, for us to have multiple vertical asymptotes. So we could have 2 vertical asymptotes or 3 vertical asymptotes, or we might not have any. It is possible for us to have no vertical asymptotes. For the second part of this, if I want to find the horizontal asymptotes, we said a function has a horizontal asymptote if the limit as x approaches positive or negative infinity of our function, if that approaches a finite value. So I'm going to look at the limit as x approaches infinity of my function f of x here. So I'm going to take this unsimplified version now, and I'll show you why in just a moment. I want to look at the limit as x approaches infinity of x squared minus 9 over x squared minus x minus 12. So remember, we talked about this in our last video. If x is approaching positive or negative infinity, and we're working with a rational function, we want to identify what is the highest power, what is the leading term of our numerator, and what is the leading term of our denominator. In this case, it's x squared and x squared. And we can just look at those two parts. We can say, okay, this is the same as limit as x approaches infinity of x squared over x squared. This one works out really nicely. It cancels x squared over x squared. That's just 1. So limit as x approaches infinity of just 1. And this part, 1, doesn't depend on x. It doesn't matter what x is approaching. It's just going to give me back 1. So that means that y equals 1 is our horizontal asymptote. So we have a horizontal asymptote at y equals 1. If we had ended up with, say, positive or negative infinity, that would tell us that we have no horizontal asymptotes. But if you end up with any finite number, be it 1, 2, 3, could be 0, or a negative number, your horizontal asymptote is y equals whatever that finite number is. Now, we could also have a horizontal asymptote in the other direction. So we could also have a horizontal asymptote as x approaches negative infinity as well. And we would approach this problem very much the same way. We'd use all the same tricks that we used last time by identifying the leading terms. So that would give us limit as x approaches negative infinity, x squared over x squared. But it's going to simplify actually exactly the same way. I know that x squared over x squared, last time we said, well, that's just 1. So this limit would also be 1. When we are working with rational functions, we really only need to check one side. And this is nice. We are really only going to need to check one side. So you either need to check the limit as x approaches positive infinity or the limit as x approaches negative infinity. That doesn't necessarily mean that those limits are always going to be the same, but it will tell us the same behavior. So what that means is if we end up with 1 on one side, we will end up with 1 on the other side. But if we ended up with, say, positive infinity on one side, we wouldn't necessarily end up with positive infinity. We might end up with negative infinity on the other side, but the behavior would be the same. We would still not have any horizontal asymptotes. Let's take a look at one more here. We've got h of x equals x squared plus 11x plus 10 all over x plus 1. So I would encourage you to pause the video here for a moment and try this one out. See if you can find your vertical asymptotes and your horizontal asymptotes. And I'll warn you, be careful here. I am trying to trick you a little bit on this one. So if I wanted to start with vertical asymptotes, first thing I'm going to do is factor. So let's see, if I want two numbers that multiply to be 10, add to be 11 would be x plus 10 and x plus 1. My denominator, since it's just x to the first power, I can't factor it. I'm just left with x plus 1. So once again, we have a common factor that cancels from our numerator and our denominator. If we took that and set it equal to 0, that would tell us the location of a whole, but we only care about asymptotes right now. So this is really just x plus 10 over 1, or just x plus 10. So for your vertical asymptotes, normally you would take whatever your denominator is and set it equal to 0. But in this case, there is no power of x there. It's just a 1. And if that's the case, if you end up with no powers of x in your denominator, or if you set your denominator equal to 0 and you end up with no solutions, well, that means that we have no vertical asymptotes, or we have none. So there are no vertical asymptotes for this particular equation. For the horizontal asymptotes, I again only need to look at the limit as x approaches positive infinity or negative infinity. We're going to get the same information either way, since this is a rational function. So if I were to look at the limit of x squared plus 11x plus 10 divided by x plus 1, again, I'm going back and I'm using that unsimplified version of my function. Here, let's see, the leading terms, that would be x squared in the numerator and x in the denominator. So this is the same as limit as x approaches infinity. Here I've got x squared over x. We can simplify that. We can cancel a power of x from both our numerator and our denominator. So this is limit as x approaches infinity. That would leave us with x over 1. Or if you just wanted to write that as x. Well, if x is approaching infinity, that means that this x will also approach infinity. So our limit in this case would be positive infinity. If we end up with either positive infinity or negative infinity as our limit in this case, that means that we have no horizontal asymptotes as well. So it is possible for us to end up with a graph that has no vertical asymptotes and no horizontal asymptotes. Or we could end up with a graph that maybe has some vertical asymptotes but no horizontal asymptotes, or vice versa. There's a lot of different possibilities that we could run into here. But please make sure you practice these skills, because it is something that we're going to come back to later in the course. We are going to have to know how to find our vertical and horizontal asymptotes.